Now we're going to talk about when do we access devices. So the operating system needs to know a bunch of things about I/O devices. It needs to know when the device needs attention. So for example, if we have a network device and a packet of data has arrived, we need some way to tell the operating system there's data available to process. The operating system needs to know when a device has completed an operation. So if we're doing a write to a disk, the OS needs to know when that write is finished so that it can be certain the data is safe. OS also needs to know if the device has encountered an error. So if you're using a network and the network disappears, the OS needs to be told that that access to the network is no longer working. There are two ways we can do this to have the operating system know what's going on with the device. The first is called polling. In polling, the device puts its status somewhere, and the operating system just checks and checks and checks for it to change. In fact, it keeps checking over and over again until the device changes its status. The other way to handle this is through interrupts. So in an interrupt, the device waits until it's ready, and then when it's ready, it signals an interrupt, and signaling the interrupt gets the processor's attention. Once the processor gets an interrupt, it then jumps to special code called an interrupt handler that handles the event. So here's an example of polling. You can see we have some code here, and it says while read status device ID equals 1, we just wait. So this is going to sit there reading the status of the device ID, and it's going to do nothing until the status changes from 1. So presumably 1 means the device is busy and it's waiting for it to be unbusy. So why is this code good? Well, it's simple. The processor's in complete control. We know exactly what's happening in the machine because the processor just sits there checking the status. Why is it bad? Well, the CPU has to poll all the time to detect the change. Where are you going to put your code? So if I want to write code that's doing a calculation, and the operating system has to sit here reading the status all the time to see when the device is done, it's not going to be a very efficient calculation. Let's take a look at some of the overheads we can expect from polling. So here we have a 2 GHz processor, and we're going to assume it takes 100 cycles per polling operation. We're also going to assume that switching between the operating system and the program is free. So it takes 0 cycles to switch to the operating system to check. So let's take a look at how much of this processor time we have to spend to watch the mouse. So the mouse needs to be polled 30 times per second. Each time we poll it, we spend 100 cycles. So that's 3,000 cycles per second that we're going to spend checking the mouse. Now that's 3,000 cycles per second out of 2 billion cycles per second, so that's 0.00015%. It's a teeny amount of the processor time to poll the mouse. So that's clearly not a problem. Let's take a look at another example, a hard disk with a transfer rate of 50 megabytes per second. As we saw in earlier parts of this lecture, 50 megabytes per second is in the low end for a hard disk these days. So if we're going to transfer this in 4-byte words, we need to poll 50 megabytes per second in 4-byte transfers. That's 12.5 million transfers per second. So that's going to be 12.5 million cycles for 12.5 million pollings per second. Each polling takes 100 cycles, so that's 1.25 billion cycles per second to do this transfer. As a fraction of our total processor cycles, that's 63% of the processor cycles just to transfer this data. So clearly this is a ridiculous amount of the processor time for transferring data from the hard disk. So why interrupts? The reason to do interrupts is because polling is not very efficient for devices that transfer a lot of data. And we should also note that in the previous example, we assumed it was free to switch between a program and the operating system, when in reality it takes a lot of cycles to do that. So those results were very optimistic. So polling is where you say, are you done yet? Are you done yet? Over and over again until the device is done. What we're going to do is look at interrupts. And in interrupts, you tell the device, tell me when you're done, and then the processor can go off and do something else until it's finished. So an I/O interrupt is just like the exceptions that we looked at before. It's asynchronous because there's an external I/O device which is saying, hey, I've got a network packet, now I need to interrupt. And you also need more information than just the interrupt. So if you get an interrupt from a network device, you need to find out what does it mean. Does it mean you have data, or it's done sending the data, or there's an error, or what is going on? So let's take a look at interrupt-driven I/O. So here's an example. Here's our code. So our program says, while we're not done, calculate the next answer. So here we are writing the code that we want to run in calculating our answer. There's also code here called handle IO interrupt. This code is what is known as the interrupt service routine. This is the code that is going to take care of the interrupt when it happens and handle the IO. So let's take a look at how this works. Here's our memory with our user program and our interrupt service routine. We're going along executing our user program until we get an IO interrupt. When we get an IO interrupt, we save the current PC so we can return to the user program later. We jump down to the interrupt service routine. We start executing the interrupt service routine until we're all done handling the IO, and when we're done, we then return back to the user program. So we've interrupted the user program and jumped to this interrupt service routine to handle the interrupt. So why is this good? Well, the user program is only halted when there's a real need. We don't need to sit there in our user program constantly polling to see if we have any IO. Why is it bad? Well, we need special hardware for these interrupts. We have to save the processor state. We're interrupting the program, so we have to save registers and we have to remember where to return to. And we can have multiple interrupts at the same time. So when we're processing this interrupt, we could have another interrupt that happens. And how do we handle that? When we were polling, we were only checking for one thing at a time, so we didn't have to worry about multiple things happening at the same time. So let's take a look at some interrupt details. So for interrupts, we need to know which device generated the interrupt. And there are generally two ways to do this. The first is we can have what are known as vectored interrupts. That is, we have a different address for each interrupt service routine for each device. So when a particular device generates an interrupt, it jumps directly to its interrupt service routine. The other approach is to have a status register. And what we do with the status register is we check it when an interrupt occurs, and based on what's in the status register, we jump to the right interrupt service routine. We also need to handle priority. So we can have multiple interrupts at the same time. For example, if we have network data coming in and somebody pressing a key on the keyboard, which one do we handle first? We have to prioritize this. And there's the tricky issue of handling multiple interrupts at once. So what happens if you press a key when the disk is reading? Well, there are two ways to handle this. The first is masking. That is, while we're taking care of the disk read, we can disable all the other interrupts, and then we won't get that keyboard interrupt. Of course, we'll lose it. The other option is nesting. So while we're taking care of the disk interrupt, if we get another one, we'll interrupt the interrupt. So we can get multiple levels of interrupts. So what happens if we disable an interrupt and it occurs? Well, nothing. I mean, if we disabled it, we're not going to get that interrupt. But if that interrupt was telling us that data is available, we'll miss the notification that data is available. So what are the operating system's responsibility with respect to I/O? So the I/O system has three characteristics, and the operating system is responsible for taking care of these. The first is that it's shared. So we have multiple programs running on our computer, and they all share the same I/O system. They share the same network, the same disk, the same keyboard. The I/O system causes interrupts, and these have to be handled by the operating system because they're privileged resources. That is, we can't let any program just access the hard disk directly because it could overwrite files that it's not supposed to access. The I/O system is also very complex. If you've ever looked at writing a device driver, that is the code that takes care of how to actually send data back and forth to a device, you know that these are very, very nasty. They're tricky code with lots of difficult things to get right, and every piece of hardware is different from every other. This is very complex to make these things work correctly. So the operating system's job is to hide this and provide a nice interface. So it needs to provide protection to the shared resources. That prevents your web browser from overwriting your operating system on the disk, for example. It needs to provide abstraction. So we want to hide all the dirty details of how do you access something. If I'm saving a file to a disk that's on the network, or a hard disk, or a flash disk, it should be the same for the program. The operating system needs to translate that into how do I actually write the bytes. The operating system also needs to handle the interrupts and respond correctly. And it needs to share the resources fairly. So if I have two programs that are both trying to access the hard disk, the operating system is responsible for deciding who gets to go first. And of course, it needs to get the best performance. If I have a whole bunch of accesses to the same hard disk, the operating system can go in and figure out what's the best order to put them in to get the best performance. So question, how do you get really low latency? This comes up in stock exchanges, where they need to process network data, that is stock transactions, with the absolute minimum latency. So what is the best way for them to detect new data with the absolute minimum latency? Well, the answer here is polling. So if they use polling, they can detect the new packet really fast. They don't have the overhead of jumping into the interrupt handler and the operating system and returning. However, when you're polling like this, you're going to waste a whole processor core doing this. So that processor is just going to be sitting there polling the whole time. And the reality here is that these people earn so much money that they don't care if they waste a whole processor core just polling. What they care about is getting the lowest possible latency. So, is missing an I/O interrupt a problem? The answer here is maybe. So for a lot of things, if you miss the interrupt, you'll lose data. So if you're reading data from the disk and you get an interrupt saying the data is ready, and you don't notice that interrupt, you're going to miss the data. However, there are some devices that lose data all the time, and if you miss data, you'll eventually get a resend of the data. So for example, if you're using the internet over a network, it expects that sometimes the data won't appear and you'll have to resend it. However, if you miss the interrupt and you have to wait for that resend in data, it will hurt your performance because you're going to wait a long time.